Hi, everyone. Welcome back. In this video, what we're going to do is we're still in chapter 7, and we're going to talk about some other molecules or compounds which would undergo substitution and elimination kind of reactions. Okay, so just to set the tone here, so far in chapter 7, we've been talking about alkyl halides. Okay, these compounds have been the topic of our discussion, and we saw how alkyl halides, these can react with nucleophiles. Okay, alkyl halides would react with nucleophiles and undergo substitution reactions. And they can react with base. They can react with a base, a strong base, and weak base and weak nucleophiles too, if we're talking about SN1 and E1 reactions. But from my last video, realized that SN1 and E1 reactions, they compete with each other. They happen simultaneously, so they're not very synthetically useful. Okay, and what I mean by that, as I said in my last video, is if I want to make one compound, if I want to make one product from an alkyl halide, I will not use an SN1-E1 reaction because it's going to give me a mixture of products. Whereas if I did SN2, then I can get one pure product. If I do E2, then I get a pure product. Okay, so they can react with a base, and they will undergo elimination reactions to give alkenes as products. So the key thing, or the important thing about alkyl halides, the reason why they undergo reactions like this, is the fact that they contain this halogen. The halogen is what enables these reactions. And going back to some of the introductory material from chapter 7, the role that the halogen plays here is that it's a good leaving. It's a good leaving group. Okay, so it's a leaving group. In fact, it's a good leaving group, and therefore it allows us to do these reactions, substitutions and eliminations. So what we're going to do in this video and in a subsequent video is look at another molecule. There are others that can be used, but we'll look at like another functional group. So the halogen is a functional group, another functional group that would allow, or that could undergo these reactions. Okay, so this functional group that we're talking about is an alcohol. Okay, so alkyl halides versus alcohols. So we're going to see how alcohols could undergo similar reactions, substitutions and eliminations, and give us some products. But then if you think about alcohols, and let's write out a reaction for a substitution reaction. Let's say we react an alcohol with a strong nucleophile. Okay, I'm going to basically introduce two possibilities here. Okay, two things that could happen. Okay, so one of the things is, okay, the nucleophile is going to come and attack. Okay, it should come and attack this alpha carbon. Since the hydroxyl is our functional group, this will be our alpha carbon. And if it works similar to alkyl halides, we expect that halide to leave. So in this particular case, the hydroxyl group should leave with electrons as a hydroxide ion. So what we would get is, we are going to get the nucleophile now connected to the alpha carbon. Okay, so this was the alpha carbon here, that's the alpha carbon here, and plus we're going to get hydroxide, okay? But the problem here is that hydroxide, this is a bad leaving group. In fact, it's a very bad leaving group. It's a very good nucleophile, okay, but it's a really bad leaving group because it's not stable by itself, unlike a bromide, which would stabilize itself. Realize that from chapter 3. Bromide is the conjugate base of a strong acid. Hydrobromic acid, HBr, is a strong acid because Br minus is a very stable conjugate. Not so with hydroxide. Water is not a strong acid relative to HBr or something. Now, water would be a strong acid compared to like other molecules, but compared to HBr or HI or HCl, water is a very weak acid. And its conjugate base, so the conjugate base of water is hydroxide. So it's not a very stable species when you compare it to halide ion in general. And so what that means is the hydroxide could basically come back and attack this alpha carbon, and whatever this nucleophile is, this could get kicked out. And you're going to get equilibrium, but you won't get to like completion. And depending on what this nucleophile is, it is possible that the reaction is actually favored in the backward direction. So that means there isn't like a lot of reaction going on at all. Okay, so that's an issue. So the hydroxide here, okay, when we think about alcohols as substrates now for substitution kind of reactions, one issue that we run into is that hydroxide is a bad leaving group. Okay, that's one of the issues. The other possibility here is realize that most nucleophiles, they're also basic to some extent. Now their base strengths vary. Sometimes a nucleophile could be a really bad base. Sometimes it could be a really good base, or sometimes it could be like an okay base. So that means when we have this nucleophile here, it is basic to some extent. And the alcohol molecule here, it has an alpha carbon. And yes, it is del positive at that alpha carbon. But the oxygen is del negative, and it's also connected to this proton here, okay, which is also del positive. That means this nucleophile might as well, or it could as well, act as a base. It does not have to behave as a nucleophile, because most nucleophiles, generally, nucleophiles, there are exceptions to this, but generally, nucleophiles are also decent to good bases. So that means a nucleophile could do an acid-base kind of a reaction, where instead of attacking the carbon here, which is what we're looking at here in the top equation, and it's actually behaving as a nucleophile, now the nucleophile, instead of acting as a nucleophile, it could act as a base, and it would go for that proton on the hydroxyl group and just do an acid-base reaction. So what we'll get at the end is going to be an alkoxide plus the conjugate acid of this nucleophile, because the nucleophile is acting as a base. So make the conjugate acid. And then again, you know, the alkoxide can go deprotonate and the electrons go back to that. So that means since it's an acid-base reaction, depending on which is the strong acid, you're going to get equilibrium here. And so what that means is, because of both of these scenarios, we're not getting reactions. We're not going to get good reactions like alkyl halides, like substitution reactions. And similar situation would apply to elimination reactions. We won't get a good substitution or a good elimination reaction if we used the alcohol directly. And notice that the problem here is that the hydroxide is not a good leaving group, or it is a bad leaving group. And secondly, it is acidic, okay? It has a proton in it. So that means if we have to use an alcohol as a substrate in SN2 or E2 kind reactions, we have to actually change this alcohol to make it a good leaving group. Okay, so that is what we're going to see in these videos, this one and the next one. So alcohols as substrates in substitution and elimination reactions. Okay, how would we do this? So the first example is, or the first strategy that is used is what we're going to see in this video. The second strategy, we'll see that in a subsequent video. Okay, so the first strategy that's used is to convert an alcohol to an alkyl sulfonate. Okay, an alkyl sulfonate. That means this is an alcohol. This is converted into some Z over there. This is an alkyl sulfonate. Okay, this is an alkyl sulfonate. Now, in case of an alkyl sulfonate, so we'll see how an alkyl sulfonate is synthesized, but in case of an alkyl sulfonate, notice again that this alpha carbon, which is the same as here, okay, that's the alpha carbon in the alcohol, and that alpha carbon is also there. This alpha carbon is still del positive because that oxygen is del negative. Okay, so our leaving group in an alcohol would have to be the hydroxyl group, but in a sulfonate, our leaving group is the sulfonate ion. So that is the sulfonate ion. And so now when we draw it out, we're looking at hydroxide. That's our leaving group. Okay, the hydroxyl group, sorry, is the leaving group. And when it leaves, it becomes a hydroxide ion. Similarly, here the sulfonyl group is our leaving group. And once it leaves, it's going to become a sulfonate ion. Okay, so this is what the leaving group becomes. And as you could notice now, this sulfonate ion is actually resonance stabilized. In fact, it has several resonance forms, which means it is stable. And if it is stable by itself, then it is a good leaving group. So that's pretty much what we saw in alkyl halides. They were stable by themselves, and so they were good leaving groups. The reason why a hydroxyl group in an alcohol was not stable is because it became hydroxide, which is not stable by itself. So it's a bad leaving group. But a sulfonate ion, it can do resonance, several resonance forms within itself. And so it basically delocalizes that charge. And so for that reason, the sulfonate ion is a good leaving group now, okay? So that's one strategy that's used to convert an alcohol into a good, better leaving group. Okay, so now we'll see how do we do this reaction. Okay, now we will not be going into the details like a lot because I think the mechanism is still, it is very different from the kind of mechanisms we'll be seeing this semester. But the mechanism of this would make more sense when you go to alcohol chapter in 3150. Okay, but synthesis of alkyl sulfonates. So the way this is synthesized is you react your alcohol, okay, you react your alcohol with a sulfonyl chloride. Okay, so we're going to write this as Z. So Z is some group. Okay, I'm not writing it. I might as well write an R over there because it is some carbon containing group also. Okay, so this is another carbon containing group. Okay, so most examples, Z is basically a carbon containing group, and I will write down some examples of what Z could be. Okay, there's some carbon containing group. So you react your alcohol with this molecule, which is called a sulfonyl chloride. Okay, it's a sulfonyl chloride, and this reaction is usually done in presence of a base. The most common base which is used is pyridine. Okay, pyridine is this molecule here, which is a 6-membered nitrogen containing ring compound, and it's aromatic. We don't know any of those terms, but it's pretty much like benzene. Substitute one carbon with a nitrogen atom. Okay, so there's a nitrogen atom here. That's what pyridine is. And so when you do this reaction, what you get is O. So this O is actually coming from your alcohol. Okay, that Z. So that's an alkyl sulfonate. Okay, that's an alkyl sulfonate. Z, some examples of, okay, there is a byproduct that's formed with this. Okay, there is a byproduct that's formed here. Plus, we're going to make pyridinium chloride. Okay, that's the byproduct that's formed. So the pyridine acts as a base. So in the mechanism of the reaction, at some point, it basically grabs that proton. So the nitrogen gets positively charged, and the chloride ends up with that positively charged cation, essentially. Okay, it's not a carbocation, it's a nitrogen-based cation. So it ends up there. We call it pyridinium chloride. Okay, that's what happens here. So in terms of Z, let me write down options for Z here. Okay, so Z could be, some of the examples is, it could be a methyl group. It could be this group, so methyl, it could be a, there is a methyl group here, there. It could be a CF3 group. There are other options possible. So there are several options possible, and I've written Z just to basically include any of these options. Now, the most common one that we will be seeing, okay, the most common one that we will be seeing is when Z is this group, okay, that group. So when Z is this group, which is a methyl group on a benzene ring, this reagent here is going to look like that. So Z is all of this connected to that sulfur. So this bond is basically what's connected to that sulfur here. Okay, and in this particular case, this is called a para-toluene sulfonyl chloride. Okay, para-toluene sulfonyl chloride. And this is abbreviated as TSCl, tosyl chloride. Okay, just call it tosyl chloride. And I think I'm running out of space here. I'm going to erase some of this here. In fact, maybe all of this. Let me write this again. So when you react the para-toluene sulfonyl chloride with an alcohol in presence of pyridine, that's the base. So notice how I'm writing reactions in different ways, and in every case it basically means this is reacting with that alcohol, this is present. I could write the alcohol here and the pyridine could go over there. So do not memorize a certain pattern of how things are written. You have to look at everything that's on the arrow, above it, on side, you know, whatever that means. So you're basically looking at everything to identify what's going on there. So this is still an alcohol reacting with para-toluene sulfonyl chloride in presence of a pyridine. And in this particular case, our product is going to look like that. And this molecule here, just to abbreviate it, because so notice para-toluene sulfonyl chloride is abbreviated as TSCl. So that means TS is all of this. That's what TS is. So our product here, all of this is TS. Okay, all of that is TS. So that means our product can be written as ROTS. Okay, that's our product. And so this is the most common. And again, realize that this would have the pyridinium chloride that's formed. I'm basically ignoring that right now. We've seen that in the previous previous slide, essentially, or on my board work, essentially. Okay, so this is what our product is going to look like, and you're always going to see it abbreviated as OTS. So that is this group. All of that is basically our leaving group, the good leaving group. Okay, so OTS, and this molecule, like the general name for a molecule like this is a tosyl ester. Okay, we call it a tosyl ester essentially, with some alcohol. So it's an ester of tosic acid. I think all of this you will see in 3150. Okay, but kind of realize that something like this, what we're trying to say here is this tosyl ester is the equivalent of an alkyl halide. Treat this tosyl group basically like a halogen. It's a good leaving group. Okay, That's essentially what we're seeing here. So now let's look at a few examples. Now that we know how a tosyl group is made, okay, let's look at a few examples where a tosyl group would undergo substitution and elimination reactions. Okay, so, and I will show you one example of each, okay, of what would happen. Okay, so let's say we have OTS, and you react this with sodium cyanide. Now, on a quiz or an exam, this positive and the negative might not be written, so please get used to identifying where the positive is and where the negative is. And notice that we've been doing this from chapter 1 or 2 essentially, so whenever you have sodium, potassium, lithium, any of those things, those are cationic, and so the group with it is usually anionic, okay? So what we have here is, and some solvent, but I'm not showing the solvent here. Could put it down, but doesn't matter. So this is a tosyl ester. This tosyl group is a good leaving group, okay? That's our leaving group essentially. And our alpha carbon is this. And so essentially what we have is a primary tosyl ester here. And we have sodium cyanide, which is a good nucleophile, okay? So primary related to alkyl halides, primary alkyl halide, primary tosyl ester with a good nucleophile. This would undergo an SN2 reaction. So the cyanide is going to come attack, and so our product is going to be a nitrile where the cyanide is now connected to that alpha carbon. Plus, we will have Na plus and OTS minus, okay? So that's a reaction. Second example. Let's look at another SN2 actually. OTS. Okay. Now, actually, one thing I want to point out here is, let's say if we start with an alcohol like this, a chiral alcohol, and you react it with TSCl, so the para-toluene sulfonyl chloride, in presence of pyridine, you will make the tosyl ester. So the tosyl ester that's formed is going to be of the same configuration. It's going to retain the configuration at this carbon, okay, the alpha carbon. That does not change because when we do this reaction, we are not doing anything to the bond between the carbon and the alpha carbon and the oxygen. So since that bond is untouched, the stereochemistry at that carbon should be retained in the product. So this is what we're going to get. That would be our tosyl ester. And so now, if you take this tosyl ester, okay, and then with this, remember as a side product, you're always going to make the pyridinium chloride. So that's our side product from this first reaction. Now, if I take this tosyl ester and I react this with sodium cyanide, again, I use the same reagent. Sodium cyanide, this is a good nucleophile. So it's going to do an SN2. And now in this particular case, it's a backside attack. So the tosylate behaves exactly like a halogen. And it's an SN2 reaction that we're talking about. So that means when we get our product is going to come, it will form with an inversion of configuration. Okay, it's going to be of the opposite configuration. So the cyanide now basically attacks from the backside. So we're going to show that inversion because SN2 proceeds with an inversion of configuration at a chiral alpha carbon. Okay, so that would be the example for that. Let's look at some more examples. Let's change this out. And I want to use OTS. Let's say if we start with this OTS and we do a reaction with sodium hydroxide, let's say, and we'll say this reaction is going on in water. But either ways, this is a secondary tosyl ester. Sodium hydroxide, it's a good nucleophile or strong nucleophile and a strong base. Secondary tosyl ester, which is the same, is equivalent to a secondary alkyl halide. It would have a higher preference to undergo E2 reactions, okay? Because secondary alkyl halides, they undergo SN2 reactions the least reactive or the slowest, okay? They're the least reactive in SN2 reactions because you start with methyl, then primary, and then secondary. Whereas for E2 reactions, it's tertiary and then secondary. So they somehow rank second, okay? So they have a higher propensity to undergo E2 reaction. Plus, we are using a polar protic solvent, so that's facilitating the E2 reaction here. So in this particular case, our product that's going to form, we have, this is our alpha carbon, we have beta, and we have beta prime carbons. So we have H beta prime, and we have H beta. And so our products are going to be this, the transalkene plus the cis-alkene plus that monosubstituted alkene. So these are both coming from the beta carbon, alpha, beta, this is alpha, that's beta prime. And along with this, you cannot rule out an SN2 reaction. So you're also going to get some SN2 product here, okay? So it's not like you can basically favor one over the other completely. There's going to be a competition, but E2 is going to be more favorable, okay? So our E2 products here would be the ones that would be formed in a higher quantity. I hope that's good. Okay, so we will get these products, all of those. That's E2, and this is our SN2 product. All of those are E2. And among these E2 products, the trans disubstituted alkene is still going to be our major product. So Zaitsev product, none of that changes because it's an E2 kind of mechanism. So all of those things still apply. Okay, so that was example number 3, actually. So what we're going to do is we're going to look at maybe 2 more examples here. So example number 4, let's say we have a tosylate like that. And we react this with sodium methoxide in methanol as solvent, and you could heat this, okay? Let's say those are our conditions. So this is a tertiary tosylate, so similar to a tertiary alkyl halide. What we have is a strong nucleophile, strong base with a polar protic solvent. So all of those conditions are favoring E2 reactions right now, okay? And plus, this is tertiary, so there is no SN2 on that. So again, this is alpha. It has 2 unique beta positions, beta and beta prime. Okay, so our products here are going to be this tri-substituted alkene, and plus we will have alpha and beta prime a di-substituted alkene. Those would be our products. The major product is going to be the tri-substituted alkene. Okay. For the same tosyl ester, if you react this tosyl ester with potassium T-butoxide, let's say, now we have a tertiary alkyl halide with a bulky base now. So these products are Zaitsev products or Zaitsev elimination there. With a bulky base, we are looking at a Hoffman elimination right now. So that means we're still going to get both of those products, this plus the di-substituted alkene plus the tri-substituted alkene, but now our major product is going to be the di-substituted alkene because Hoffman elimination favors less substituted alkene. It would prefer to get, deprotonate at the primary beta carbon compared to a secondary beta carbon. So sterics is the key. So we discussed this in the video on E2. So whenever you have a bulky base, it would like to go for the less substituted beta carbon to deprotonate. And the major product would come from there. So we get Hoffman product there. So behaves like alkyl halides essentially. Okay, one last example here. And we'll use this same alkyl halide that we had. OTS with, let's say, methanol and heat. Tertiary tosyl ester with methanol, which is a solvent. It's a weak nucleophile, weak base. We are heating all of this. That means this reaction here is SN1 and E1 competing with each other. So our products here, and the mechanism itself does not change. Everything is the same. The tosyl ester would basically act as a leaving group. So our product here is going to be, this is our SN1 product plus we're going to get our E1 products, which are these alkenes. Both of these are our E1 products. So everything is the same as alkyl halide. So you basically treat that tosyl group as an alkyl halide, and it's going to give you a similar sort of reaction. Okay, so that is everything about the first strategy, okay, where the alcohol is converted into a tosyl ester, and then we use the tosyl ester for doing the reactions. Now we'll look at another approach which would help us convert alcohols into good leaving groups in a subsequent video. Thank you.